And you could see the preamble. There's a shortcut to the tedious process in the previous example. So you already know it'd be like pulling teeth. It's called the binomial theorem. Basically, it's accounting for the probability that you could have a certain number of positive outcomes among a certain number of trials. All right. So let's say, for example, going back to the birth question, if I had, I'll even keep it simpler. If I had 10 births or even 5 births, if I were to say what's the probability of getting 5 girls out of the 10 births? You know, like a logical question might be, well, which 5? Right? Because each birth is associated with a parent potentially. And so if that's the case, having the first 5 births yield girls and the second 5 yield boys, that's a different outcome than the other way around because of the expectations of the parents. Like, I mean, I painted the bedroom blue. I'm parent number 2. You just told me I had a girl. I got some work to do, all right? As opposed to the other way around where I got a boy, I don't have any work to do, all right? So the ordering of the outcomes do matter, right, when you're dealing with probabilities, and so this accounts for that, right? But in order for something to be considered binomial, you have to meet these 4 conditions. Now, this is when I was talking about the simulations before, I mentioned that question on the test would be a gift. This is another gift. There is a question on the test that's just, and it's on every previous version of it. It'll be on every version of the test that I ever create that just simply asks you to write the 4 conditions necessary for a distribution to be considered binomial. It's usually question number 2, right? But it's all I'm asking you to do is write these 4 things. All right, so most people just write those things right on their index card and highlight it and make sure that they're ready to go. The one thing that I would caution you about is there are 2 sets of 4 things on this handout. Don't write the wrong one. Right? So it's this one, fixed number of trials, fixed probability, independent events, 2 outcomes. This is just telling you what all the values in the binomial formula mean. This is not the 4 conditions for a binomial condition, aside from the fact that this says conditions right next to it. These are the 4 that I'm asking for. Because I've had numerous people over the years write down these 4, and they're shocked that they lost full credit. All right? And it's really a gift, because I make it a 4-point question. I give you 1 point for each one of these conditions you write down. All right, that's how important it is, because I talked about this before. Probability is never going to be difficult because of the math. It's never going to be difficult because of the numbers that you have to add or multiply or anything like that. It's only difficult because you look at a problem and you say, I don't know what I'm supposed to do. I don't know what technique applies. If you know the 4 conditions, then you know when you're dealing with a binomial probability question. All right. So fixed number of trials, if I'm looking at this example, given 4 multiple choice questions, all right, that's my fixed number of trials. I'll write it up here. 4 questions. And then I'll start the process of making that look like the word questions. Fixed probability, each with 5 choices. All right, each with 5 choices. So the fixed probability is your probability of success. So probability of getting it correct. If it's a multiple choice question and there are 5 choices, what's my probability of getting it correct? 1 over 5. Independent events. All right. Now that part is it's a little harder to write out and justify, but you can just consider it. Independent events means that a second event occurring is not impacted by success in the first event. All right, so if I flip a coin once and get a heads, that doesn't mean I can't get heads any other time I flip a coin. It's independent of that outcome. I always will have a 1 out of 2 chance of getting a heads when I flip a coin. All right, whether I flip it 2 times or 200 times, I'm always going to have a 1 in 2 chance. Same thing with a die. All right, but when you get into marbles and cards and things like that, if I remove a card from a deck, I have now changed the probabilities. All right, it's no longer out of 52, it's out of 51. All right, in this case, my independent events applies because I'm always going to have 5 choices. Now, there is a little gray area when it comes to this particular context because, I mean, we've all sat for tests that involve multiple choice questions. And then you have no idea how to do number 2. But then you answer number 8. And there's something about number 8 that helps you figure out number 2. You know, like who wrote the Declaration of Independence? And then you get to number 8 and you're like, knowing that, was it Benjamin Franklin? Oh man, I should know this one. Knowing that Benjamin Franklin wrote the Declaration of Independence, what was his motivation? You know, it's like, oh, I know the answer to number 2 now. You know, so there sometimes is a dependent relationship, but it's not intended. All right. God, I hope it's Benjamin Franklin. 2 outcomes, success or failure. I think that part is obvious. It's either right or wrong. All right. And so that part you might look at as also being a little bit of gray area because it necessarily has to be a multiple choice question that only has one correct answer. All right. And a bunch of wrong answers. If it's another one, if it's another type where it's like select all that apply, then that blows it all up. Or if it's one of those. No, actually, I was going to say choice 1 and 2, but not 3 kind of deals. But usually that's another choice in and of itself. So I think that's okay. All right. But based off of this situation, we now know that binomial theorem applies. All right. So what we do is we move on to the next little category here where we identify the number of trials, which we already kind of alluded to, number of successes that we want, probability of getting exactly 2 correct, probability of success on any one trial, and probability of failure. That's if you're actually using this formula. The good news is the calculator will do that for you, except the process that I wrote here is for the older calculators, the old TI-83s. So this should be, if I'm not mistaken, second bar is option A. I'm going to just verify that real quick, and then I'll walk you through it. I just want to make sure it's, yeah, second bar is option A. So make that change on your handout. Unless you have a TI-83, in which case leave it exactly the way it is.
So
This is for 84. So A, the second bar's option A is for TI-84. All right. So you need 3 pieces of information when we use this function in the calculator: the number of trials, probability of success, and the number of successes. Number of trials, probability of success, and number of successes. All right, so we're in a new menu now. Second, and then we're looking for the vars key, which is right next to clear. All right, so second vars. Whoa. That's something. What the? Why did that bounce around on me? That's so weird. Second and vars. Doesn't help that the clear is highlighted in red. You're going to go down for option A. It's the one that says binom PDF. Under distribution, yep. It should be A. Because right below that is binom CDF. That's for something else. A. Binom. So you have to scroll down right after the 0 should be where it is. And so it brings up this menu. And it asks you for the number of trials. So the same things I detailed there, but then when it gets pasted in your home screen, it's going to take on this form. So number of trials, you're going to just type in, there are 4 multiple choice questions. I'll just type it in because it's going to look like crap. Probability of success is 1 out of 5 on any one trial, and we want 2 successes. Now, if you're the one taking the multiple choice test, you want more than 2 successes, but for the purpose of this question, we're just going for 2. Then you select paste. You can see it has the same setup as what I wrote here.
So what's the P again?
Probability of success.
And what did you guys say?
1/5.
So 1 divided 5.
1 divided by 5, yep. Oh, geez. That's all right.
When I click on 8, this is what gives the one.
Oh, no, A.
Oh, 8.
So second bars and then go down to option. You got to scroll down and find that one. A,
Okay,
yeah.
thank you.
Sorry, folks. I didn't realize it was super tiny up on the big screen. It looked great on my screen. I didn't even look over.
X value was 2, right?
X value is 2, yeah.
Paste,
You just hit paste, hit enter on paste, brings up this screen, then hit enter, and then you get 0.1536.
enter, then
Then it should say 0.1536.
and press enter again.
Yep. And that tells us the probability that you will get exactly 2 questions correct if you were to guess. And you had 4 multiple choice questions. So let's say you're taking a test and there were 50 multiple choice questions. You knew how to do 46 of them, but the last 4 you had absolutely no idea and you just had to take a guess. You couldn't even use process of elimination. You just had to take a guess. You guessed on 4 questions, the probability of you even getting half of them right would be not even 16%. All right, so basically this is saying you're screwed. You know, so.
In my calculator, I got different numbers. I mean, but I got the 1536 along with other numbers. Did that supposed to show up or not?
Yeah, if you could.
Press enter. See, all this, got the 1536 is there.
Oh, because you need 4 comma, I think you just didn't put the 2 in.
2, okay. So go up, and how do I put the 2
Well,
in?
clear it out, and then do it again. So second bars, go to A. Yep,
Enter?
enter.
This
Now,
was 4.
for X value, put in the 2.
Okay, 2.
Then go to paste.
And then press enter.
Yep,
And then enter again?
yep,
Okay.
and there it is.
Perfect, thank you.
So I just learned something based off of that interaction. So let's say, just going back to the, because I was just going to show you this really lengthy, convoluted way of doing this, and I just learned a much easier way. So going back to that unusual results question, because this was binomial. This, I didn't mention it then, but it was definitely a binomial situation, because you have 14 pregnancies. So that's our fixed number of trials. You know, it's disturbing to kind of refer to it that way. You know, like to think of somebody's life-changing event as a trial. Not even like a trial and tribulation, but like a trial and an experiment, right? So, but it is, you know, we're just looking at the probability. Fixed number of trials, 14. Fixed probability, we assume 1/2, right? Independent events, right? If one person has, you know, the first birth is a boy, for example, that doesn't mean that boys are no longer available to the other people. So independent events and 2 outcomes, boys and girls, at least academically. The real world's not always gonna, it's not always gonna merge and jive with the academics. So we do what we can. But anyway, if that's the case, then what we could do is apply a binom PDF to this to come up with this entire distribution. All we would have to do is binom PDF, PDF, "14 trials, probability of success," which would be getting a girl in this context. And then I would not put in an X value indicating the number of successes. And what that'll do, and this is the thing I just learned, is it'll give me all of the possible outcomes. So second vars, go down to binom PDF. Type in your 14, your 1/2, and leave the X value blank. It's crazy because, like I said, I just learned this 2 minutes ago, but now in every other class it's going to be like, well, of course you would do it this way. Why wouldn't you? So hit enter. Enter again, and it gives you the full-blown distribution, but it's giving it to us in scientific notation, which is pretty hideously ugly. But this is telling us what the distribution really should be based off of the natural occurrence of things. So if I'm rounding it, the values in this table are what they would round to. So, you know, I just scrolled, the third value is 0.022, but if I'm going to 3 decimal places, you know, I wouldn't write that whole decimal value. It would just be 0.022, 0.061. You can bet that if you scrolled even more, you'd get the 0.122. If you wanted to look at the whole shebang in a more convenient fashion, you do what we did with the simulations, store into L1, and now you could have all of the outcomes in a list, a nice convenient list. All right. So I'll just kind of chuck that down here. because that's actually going to change this new information is going to change how I'm going to teach the next example. All right, so I stored it into L1, and I left the L1 values from this problem in here from before, and you can see going down the list, what we had in our table, in the given table, were all approximates. These are the real values corresponding with those numbers. All right, so this is really just saying, hey, if nature is allowed to run its course, a 50-50 relationship, then these are what the probability should be.
I'm left with paste, so.
Oh, just hit enter on paste.
I did, but it's giving me the L1 and L2 table.
Weird. You just showed me.
I did? Really?
Oh, no, so you're not even you're doing that here. Second bars.
14, you said ignore that.
Right. Paste that's in your home screen. And I have your list. And then you store it.
Stow L1.
Right. And then hit enter. And then it's all
So
going to
I'm
be.
writing the steps into
Yeah. All right, so that's how you'd come up with an entire distribution for binomials. And so this is kind of a game changer, because if I needed to know whether or not in a binomial distribution it's unusual or usual to get certain values, I don't even need the table anymore. The calculator will give me the table, and then you just run the mean and standard deviation, your one variable stats based off of your tables, and then you could just get all the information you need that way. Okay, it's a very exciting time to be alive, statistically speaking. All right, so the second example says, given 4 multiple choice questions, each with 5 choices, find the probability of getting getting at least 2 correct. All right, and then at most 2 correct. So let's use this newfound technique to get this job done. All right. So now I don't have to teach you a different function and risk confusing the daylights out of you. All right. So I'm going to clear out all this stuff because it's just going to get in the way. So at least and at most. At least is 2 or more, in this case 2. At most is 2 or less. So let's go through the distribution menu. So second, vars, option 0. So, I'm sorry, option A, wrong. Second var, so same menu, option A. We're back to this scenario, 4 1/5, but we're going to leave it blank for the x value. So this is going to give us all possible outcomes. Hit enter on paste, puts it into your home screen.
X value, what was it?
Blank.
Blank. And paste and enter.
Yep. And so what this gives us is an array of values, just like we had for the births. It's going to be much shorter though, because I'm only doing 4 trials. All right, so 4 multiple choice questions, but I'm still going to store it into a list because it's just going to be more convenient that way.
Sorry, but I pressed after paste, I pressed enter, but it's bringing the L1 and L2.
Me too.
I just can't. I'm not being able to get this. I just don't know what's going on.
Yeah, so you're supposed to be in your home screen before you
Okay.
select that.
Okay.
So
Home screen.
out of there.
Okay.
Second bar.
Second
All right, so we're going to store this into L1 and hit enter. And again, it just seems to repeat the process of giving these values, but it's behind the scenes, it's writing these values into L1. So then I hit stat, edit to access those numbers.
Sorry, you said still second, L1, enter.
Yep.
And then go back to step edit 1.
Stat, edit, yep. And then you should see all your probabilities listed there. All right, so these outcomes, these probabilities are associated with the outcomes. So what we're talking about is getting questions correct. So number correct. So it is possible that you could get none correct. You could get 1 correct. 2 correct, 3 correct, or maybe you get all 4 correct. And these are the probabilities that go along with those outcomes. So now we have a complete distribution of every possible way that you could answer these 4 questions. And you could see that it's not very likely that you're going to do well if you guess on all of them. All right, so this is a probability question, but it's also a public service announcement. Study for your multiple choice test. All right? But when they say probability of getting at least 2 correct, that means 2 or more. All right, so 2 or more would be the point 0.1536, the 0.0256, and the 0.0016. So I just have to add those together.
So these were the correct choices, right?
Of getting 2 or more correct. And I'll add those up in a minute, but I want to set up probability of getting at most 2 correct.
Why is it those numbers that I can't?
Because they're associated with 2, 3, and 4. We want 2 or more.
Okay, so you think above.
2 or above, yeah. At most 2 means 2 or less. So in this case, it's going to be the 0, the 1, or the 2. So 0.4096, another 0.4096, and then 0.1536. And at that point, it's just simple addition, which we can do. We don't need fancy shortcuts on the calculator for that. It's just add them up. So 0.1536 plus 0.0256 plus 0.0016. Then 0.4096 plus 0.4096 plus 0.1536. So these are our two probabilities, 0.1808 and 0.9728. All right. So what we're getting from this is that it's way more likely that you're going to fail if you had to guess, because at most two would be 50% of the questions incorrect or less. So almost guaranteed that it is that you would pass. And not even 20% that you would get more than 50% or 50% or more. Right? So not very likely, but it's a way of evaluating strategies, because if you think about it, like multiple choice assessments, I don't know how many people were planning on showing up for a 20 question multiple choice test without having at least reviewed some of the concepts. And even if you didn't review the concepts, I don't know that you would ignore the questions completely and just start randomly guessing. But this is justification that would definitely not work out well for you. Right. And that's it for that part, yeah. Now the that birth question. So yeah, and you can see how things can get out of control pretty quickly. We talked about 14 births. And we made a probability distribution, and it wasn't too crazy. But if it's 100 births or 1,000 births or 10,000, because law of large numbers says that if we keep increasing trials, we're going to get closer and closer to the accurate outcome, right? So if that's the case, then I would want to make the number of births as large as possible. I don't want my sample to be huge, but that doesn't mean I want to write out an entire distribution just to determine if the number 68 is unusual. It turns out there's some nifty shortcuts for determining the mean and standard deviation of a binomial situation without actually having to create the distribution like we've been doing. All right. So for that, it's just as simple as taking the number of trials and multiplying it by the probability of success. But it needs to be a binomial distribution, which means those four conditions need to apply. Fixed number of trials, (100 births), fixed probability, so we assume probability of getting a girl is 1/2. Independent events, just put a check there because we've talked about that. Just because you get a girl in one birth doesn't mean that the second birth can't lead to a girl, or the third, or the 10th, or the 900th. What the hell? Oh, hockey stuff. That is a check mark. And two outcomes. All right, so mu is equal to NP. The 100 trials multiplied by the probability of success, which is going to give me 50. So that's my mu. Mu is also the expected value. So that's easy enough. Because if you're conceptualizing it, there's 100 births. How many do you expect to be female? How many do you expect to be male? In an ideal world, I guess it would be fair. You get half and half. All right? Assuming that's how you define it. Sigma is equal to the square root of NPQ. So 100 times 1/2, which is the P, times, now Q is the probability of failure. Which is equal to 1 minus P. So 1 minus 1/2. So 100 times 1/2 times another 1/2 is going to be the square root of 25, which is 5. Dang it, that flew off. So mu plus or minus 2 sigma. If we're talking about usual versus unusual, would be 50 plus or minus 2 times 5, which is the same as saying 50 plus or minus 10. If I do the subtraction first, I get 40. 50 minus 10 is 40. 50 plus 10 is 60. So these are the usual values. Anything outside of that interval would be unusual. So therefore, 68 is unusual.